So if it wasn't for you, then you're gonna laugh when you see actually how to do it, because you're just gonna be like, oh. All right. So it says a block with a mass of 9 kilograms is pulled at a constant speed across a horizontal tabletop with a spring scale. The scale reads 61.8 newtons. Calculate the coefficient of kinetic friction. So we talked about this before, but maybe you don't remember it. But a spring scale, it measures the amount of force of something, okay? So remember what your equation of friction is. Your equation of friction is friction equals the coefficient of friction times Newton. Since it's being pulled, it's going to be kinetic friction, right? So now let's do our known values. Well, we know that our mass is equal to 9.00 kilograms. We know that the force read on the spring scale is 61.8 newtons. So what it's asking us for is the coefficient of kinetic friction, which means that the force read by the spring scale is what the force of friction is, okay? So, so this is your frictional force, because a spring scale is used in order to calculate some kind of force. It's not calculating the force of it being pulled, it's calculating the force opposing whatever it is. So in this case, it would be friction. So it's asking us to find this. So we have friction and we have mass. But if you look at this, you'll see your normal force is directly opposite your weight because it's on a flat surface, which means that normal force is equal to the weight. So all we have to do is to find the normal force is do normal force equals 9.00 kilograms times negative 9.81 meters per second squared. Since normal force is in the positive direction, we're going to take the absolute value, making sure we get a positive number. And then we're going to rearrange our problem to solve for the kinetic and friction, coefficient of kinetic friction, which is our unknown, which gives us the coefficient equals friction divided by the normal force, which gives us 61.8 newtons divided by this number, which I don't have a calculation, but if you do it in your calculator, you do,
0.69.
is it 0.69? Okay, I was gonna say 9.81. So, but this whole thing should give you 0.00 at 0.700 as your coefficient.
I was close.
What did you get?
0.69.
Yeah, so around 0.7.
Okay.
Yeah, if you got 0.699 or 0.7, you're right. Makes sense? This part's not so hard. The next one's more difficult because now we're going on an inclined plane, which causes some difference. Okay.
The tube is inclined.
Okay. Number 6. A warehouse worker is unloading a 240 kilogram crate from a truck using an ideal rope, passing over a single ideal pulley above the truck. What is the minimum horizontal frictional force that the floor must exert on the worker to keep him from slipping while slowly lifting the crate if the rope between the pulley and the man makes an angle of 25 degrees with the vertical? Okay, so this one's a little bit more tricky to visualize because you're going to have some horizontal crate was unloading 240 from a truck using ideal rope passing over a single pulley. Okay, so this is the truck. This is a truck passing over a pulley. You have a rope lifting a box that is 240 kilograms. So that's the mass of the truck. And it's asking, so this angle is 25 degrees. So this would be more at an angle. I made it look like it's directly vertical, but it says that it's being pulled at an angle. And it says, what is the minimum horizontal frictional force that the floor must exert on the worker to keep him from slipping while slowly lifting the crate? So then you have your man right here holding this rope, and it's asking you what, sorry, this angle is 25. Reading these problems can be difficult because you have to make sure that you have your frame of reference correct. So when I read it the first time, I thought that it was saying that the pulley was at an angle, but it's different. It's the man pulling the rope is at an angle with the surface on the box. Now, one thing that you have to realize here is that the tension here is going to be the same as the tension here, okay? The only difference is this one's going to be at an angle, so that's going to affect it just a little bit. So it's asking us, what is the minimum friction, okay? So if it's trying to keep him still, is it static or kinetic?
Static.
Static. So we're going to ask, what is that FS minimum? And we need to make this
FS
our...
max equals MU.
So, now, we have to do some other stuff. I have my notes on my phone, so I'm going back to make it. I just want to see what I did the first time. Okay, so one thing you're going to have to realize is you're going to have to make your angle a little different. So, because it didn't give us a coefficient of kinetic friction, right?
Nope.
Wish it did. I really wish it did. It would have been
I
a
also
lot
really
more
wish-
not confusing. To be honest.
Yeah, I'm pretty confused. To the max.
I mean,
S
once
max.
I do it, you'll understand.
Why is that act?
Why is that funny?
Was
I was
it
just
funny?
looking for
I can't
their,
tell, I don't know what he's
so, what you need to know is two things. Okay, this force, remember how I showed you that if you have your force greater than the static friction, that it's going to move? Well, in order for it not to move, you want force and friction to be equal, okay? Does this make sense? Are we clear? So
Yes.
since we want to keep the person stable, we don't want the person to move, so your force and your friction are going to be the same. Now, this box is going to matter only because it's attached to the same rope. What are we doing?
Should I throw something there?
So tension in the rope here is going to equal tension in the rope here. So that's going to be important. The only force that's pulling on this person is the rope. Does that make sense? So the only thing that could keep it from the person from being stationary is the rope. So it's asking, what is the minimum frictional force that it has to be pulling on it? So the minimum friction force that is required has to be equal to the amount of force that this person is pulling. The box is pulling, right? So if the box is pulling with the same amount of force as friction, the person will stay still. The same as when you're sitting in that desk, if the desk is pushing up with the same amount of force you're pushing down, you're going to stay in the desk. Everybody just make sure you're with me, okay? So, this means that
I wonder how much weight this desk can
friction has to equal force. So, we have to find out first what the tension in this rope is in order to figure out what this one is. Our x-axis is going to be the surface here. So you have to realize that the tension is now at an angle. the other thing you have to know is that this angle and this angle are going to equal 90 degrees, right? Because if you have your coordinate system, each square is 90 degrees. You remember that, right? So if this is pulling down at 25, you can find this angle by doing 90 minus 25, right? So when we do this, we're going to do 90 minus 25 when we calculate our component, okay?
Yes.
So, moving on. So we know that the tension in the rope, if I'm pulling something up, the weight is pulling down. The tension in the rope is going to be the same as the weight because there's no other forces acting on it, okay? So tension is equal to mg, which is equal to 240 kilograms times 9.81 meters per second squared, which is going to equal, can somebody do it on their calculator? I should have written my notes down, but they're on my computer and on my phone. I took a picture of it, forgetting that I was gonna record it.
It's 2,354.
2,354 newtons?
Yeah.
Okay. So now we know the tension, but we don't really want to know what the tension in the rope is being pulled down. We need to know it at an angle. So, let me check my notes real quick.
Then you just do like sine 25, right?
Not sine, you're going to use cosine.
Oh, I did sign.
I did sine too.
So literally all you have to do to find the force minimum is that it's going to be equal to whatever the force is that the man is being pulled on by the rope, which means that the tension is going to equal this tension at an angle of 25 degrees, but we do 90 minus 25. So this tension, which if you see tension with like a little apostrophe, that's called T prime, which is T2, or the T on the other side. So this one will be 2,354 cosine of the angle, which would be 90 minus 25. Does anybody have this?
65. Oh, wait. That's not the whole thing.
Wow.
994.84.
Right, 994.84, right? Or it could be 995 newtons.
Friction you put on that
So that's it.
It works with
The
sine.
minimum friction that keeps a person stable is going to be 995 newtons. That's all you need to know. That's the minimum amount of friction needed to keep the person from moving.
So, I don't know if it's related, but like, I did like, yeah, we use sine.
I use sine, the 2,354.
So are we pulling in the y direction or the x direction?
X.
X.
I think I just mixed them up, but I got the same answer. I don't know how.
Yeah, me too.
I think because if you took, because you did sine of 25,
Yeah.
because I think that would end up being about the same, because it's just the perspective that's different. Because if I was asking like about the weight of this, I would have used sine and I could have used the 25 because that would have been in the y direction, but I'm not. It's your point of reference. Since we're asking about friction and that's an x component value, you'd use cosine. Okay,
Okay.
so now that we've done this, does it make more sense?
Yes. Yeah.
Okay, I advise that you watch this video again, just the part of us going through it. I mean, it's nice because you can literally fast forward and like rewind the parts you want and speed it up.
Listen
But-
to our own voices.
Yes.
Yeah.
But I'm telling you because when you study this, you might think you get it right now, and then you might go do it again at home and be like, wait, what did we do again? But this way you can look back and do it. Because again, we're gonna have a test, but we didn't have any open book quizzes. We're just having these homeworks. This is all you have to study that you know of, that we've gone through. The other thing that you have is your example problems that we've done in class. You should review those as well. And we're gonna do one today. We started it on yesterday, but we didn't quite get to it. Page 182. So, page 182. I know that you're probably happy to be back and all that, Josh, but don't distract the class, okay? It's not fun.
I'm on the page. I'm on the page.
Oh, I thought I lost my calculator.
Page 182. I'm glad you didn't. That would have been such a
Where
bummer.
lost all my progress.
Okay, a 2-kilogram wheeled laboratory cart rolls without slipping down an inclined plane that makes an angle of 35 degrees with the horizontal. If the magnitude of rolling friction of the car is 0.10 Newton, what is the car's acceleration? So the first thing we do is we write our free body diagram. So we have this inclined plane. And we have a laboratory cart. A laboratory cart is literally just this little metal, it's like a really detailed box car, basically. Like, almost like a matchbox car.
Yes, so like
It's just like, it's made with like really light metals and stuff, and it's used to study force and friction and all this other stuff in the lab. And it hurts really bad when it hits your hands. And I only know that because every time we did these in lab with the laboratory carts, they would have somebody hold the incline up, and then they have another person catch the car at the end. And by the end of the lab, your hands would be like all red from
How
like
does it hurt?
catching the car. Huh?
How does it hurt?
Because it's made like from metal and it just has like sharp edges. It's not like painful, but it's just like, it's like catching a baseball that someone hit with a bat almost.
Oh.
Yeah, it's just annoyingly hurts. I don't know. But it's more like you don't want it to happen, but it's not like it's gonna hurt you so bad that it's gonna affect the rest of your day. It's just like
it's
bracing you
it's
with
just
something.
painfully
Discomfort.
and annoyance is painful.
Yeah, I get that, like discomfort or like an annoying pain. Okay. Anyways, moving on. Alright, so we have this little cart, and then we have our incline that is 35 degrees with the horizontal. And so now we have to figure out what are all the forces on our system. Well, obviously, we have the weight of the car. We always have the weight of the car and the normal force because that's what the incline is pushing back up on the cart with. Now, since we're not talking about frictionless surfaces, we also have our rolling friction because it's on wheels, okay? So then remember our x-axis is going to be the incline, which means that the force of the weight has to be broken up into its components. It's x and y components. Force of the weight in the x, force of the weight in the y. Okay. So what are our knowns? Well, we know that our mass of the car is going to be 2 kilograms. So let's find the weight of the car. Somebody, 2 times 9.81.
19.60. Yep.
Say it again.
19.62.
19.16?
62.
62.
Wow.
So that's going to be newtons,
62.
and it's going to be negative because weight is downwards. Okay. And then we know the magnitude of rolling friction of the car is 0.10. So we know rolling friction is 0.10. Then we know, then we are asked, what is the cart's acceleration? What do you think we're going to use for our equation to find acceleration?
F equals
F equals ma. Good.
M.
F equals ma. So, with F equals ma, We can't just say force is equal to mass acceleration now. We have to say the whole sum of the forces. Now, if we're asking for acceleration, is this in the x or the y direction? You know this. If we're solving for acceleration, is it
It's
Why?
or-
Why is
Because
it-
gravity is y.
right? So that's the acceleration in the y direction is gravity, so we don't have to calculate that. We know it's 9.81. So if it's asking what is the quark's acceleration, we're going to use all of the forces in the x direction, not the y direction. So, first things first. Is the normal force in the x direction?
No.
No, it's completely in the y direction, so we don't have to consider the normal force. I'm telling you this because it could confuse you. If you look at the example problem here, they're going to put n sub x. Don't get confused and think you have to consider the normal force. The normal force is 0 in the x direction, so disregard. So what do we have in the x direction then? What are some of our forces in the x direction?
Friction.
Friction, or rolling friction. And then what else?
Weight.
Then we have the first force of the weight in the x direction. So we're going to have to solve for the x component of the weight first. So we're going to use sine. The sine of the angle, which is 35, and our weight, which is 19.62. All right, somebody tell me, what is the weight in the x direction then?
11.2.
11.2?
Yeah. 2
Okay, 11.2 newtons. So, are some of the forces in the x direction?
11.3.
Oh,
He said 0.25.
oh, I'm sorry.
No.
Okay, so our rolling friction in our x,
It ain't that big.
so is the weight pulling you down the ramp or up the ramp?
Down.
Down. So we can consider that our positive or our negative in this case. But what you have to remember is whichever one you consider to be positive, you have to keep positive. If it's negative, you have to keep it negative. So what we're going to do is we're going to consider our weight to be pulling us down the ramp. You could say that that's negative because it's going down the ramp. I'm going to say it's positive just because it's the larger number, and so I'm going to subtract.
Round up now.
I'm going to subtract 0.10.
It's honestly best if you don't round up because then you get the.
Okay, so what is this value?
Minus.
That's what it says, right?
It's just going to be like 11.2, right?
Yeah.
11.2. Okay,
I'm so confused.
So-
It's so simple.
so now we have our force in the x and our MA. So we're going to say our force in the x is
Yeah, but you round
11.2.
up at the end.
Our mass is 2 kilograms.
That's why.
And acceleration is what we're solving for. So we're going to divide each side by 2 kilograms. And you're going to get 11.2 divided by 2 equals acceleration. See what you get.
5.6.
And that's the answer. 5.6.
Not good.
There you go. 5.6.
That's
And they say it's negative 5.6 since the car is going down the incline. So they would say it's negative because downward is usually negative. So you can add that direction as negative, or you could just write 5.6 meters per second squared down the incline. But as long as you indicate which way the car is rolling. But not all that difficult, right? F equals MA, write what you know, make sure you solve for any components, find the sum of the force, solve for acceleration. Any questions though?
Nah.
Trinity, do you have a question? It's okay if you do. Okay. Sometimes I'm like, If I say pretty easy, I don't want you guys to think, oh, if I say that I am confused, then she's gonna not understand. I'm just hoping this is easy because we've been doing this so much. And now the only thing we're adding is friction. So this should look familiar besides the fact that we're adding in friction. What time is it, guys?
31, 32.
32? Okay.
No, it's
I'm going to give you guys the rest of the class to work on numbers 5 and 6 on page 187 in case you guys have
You
questions.
should get some practice problems.
Practice problems for the test? I am giving you practice problems for homework.
Wait, that's it?
And your example problems in the book. And your example problems in the book. But if you work through those, I'm not going to surprise you. But make sure you study the PowerPoint. So you should know your concepts. Like for instance, if I were to ask you anything about static friction, I'm going to go back to this page. What you need to know about static friction is literally bullet pointed on 178. Static friction can be any value between 0 and a maximum value, is oriented parallel to the surface, opposes the motion of the system of interest, etc. If I was going to ask you about kinetic friction, it would probably be pulled from page 177, which has a bunch of bullet points about kinetic friction. I might ask you some questions that are pulled from the section that says friction defined. And in that case, it would be like, what is traction? Why is a rough surface, does a rough surface have more friction or less friction? Is the coefficient of friction the same for all materials? Stuff like that. But if you've been paying attention in class, you should be pretty much set. And then you'll probably have some questions about rolling friction. You might be asked, like, I don't know. Like where is the friction located in it? And you'd say like between the wheel and the road surface, something like that. But if you study the PowerPoint, which I posted on Facts, you should have all the information that we could possibly ask questions from. You study the PowerPoint and you study your example problems in the book, study your homework problems, you should be good. Good to go.
Alright, let's work as a cohesive unit on numbers 5 and 6.
Like,
That's great.